Okay, so I will start by thanking the organizers for giving me the opportunity to talk in this session. And well, what do we want to do with this talk? Well, we want to study a computer algebra-based approach to give a polynomial model for data that come from a problem in reverse engineering for gene regulatory network. We want to find polynomials that will be in normal form with respect to the vanishing idea of some given data points that actually come from the problem. And we will achieve this result without using Grobner basis or Buchberger reduction. We will only use tools coming from linear algebra and combinatorics, and this will call also a complexity improvement. The reference paper for our problem is this paper by Laubenbacher and Stigler. This is called a computational algebra approach to reverse engineering of gene regulatory network, in which they start studying this problem using computer algebra. And our idea was to improve the method proposed in their paper. So, roughly speaking, they are studying the DNA of mosquitoes by means of computer algebra, and they adopted this modeling framework of time-discrete multi-state dynamical system, and I will explain a bit what we want to have. That is, our system is composed by different states in time that are our points, our data points, and the nodes, the coordinates, or if you prefer the variables, represent the single genes. The coordinates will take value in ZP with P prime. So finite field of size P with P prime. The dynamical system we will consider is then represented by a function from Zp to the power n to Zp to the power n that sends a state, a point, to the next one. So you are representing how the state changes in time. And in particular, these values of the elements in ZP that you put in the coordinates of the points explain you how the state changes in transition, in the sense that, for example, for P equal to 3, -1 means the value decreases, 0 is the stability, and +1 is increases. We have a finite set then of points, P1, Pn, that are the states that you are going to examine. And what happens is that f of Pi, so the dynamical system, the function representing the dynamical system in Pi, gives you Pi plus 1. And it is possible to describe the function f using the coordinate functions. So using this fj for j from 1 to n, that take the point Pi and send it to Zp, so fj of Pi. In particular, my function big F is composed by f1 of Pi, fn of Pi when evaluated in the point Pi. And these coordinate functions can be seen as polynomials in Zp. So how do Laubenbacher and Stigler solve the problem? They separately compute the function fj, and then they reconstruct the whole f. And in particular, those polynomials fj are the polynomials that they want to be in normal form, reduced modulo the ideal I of x, where I of x is the ideal of points of x, and x is my set of points. In particular, what does it mean be in normal form? Well, if I have an ideal of the polynomial ring and a polynomial, the normal form of f is a polynomial of this kind, in which you are doing a linear combination of the elements in a basis. I don't know if you see the last line of the slides. Perhaps I can hide this other window. Okay, now perhaps you see it. Well, this A, in which you pick the terms, is a basis of the quotient algebra, and this difference, f minus a normal form of f, is an element of I. This normal form is the unique polynomial such that this happens. The algorithm proposed by Laubenbacher and Stigler then has 3 steps. First of all, you compute for each fj a particular solution. So it gives you the values that you want, but it's not in normal form. Then you compute a Grobner basis G of the ideal of points using the Buchberger-Moller algorithm, that is an algorithm getting the Grobner basis by interpolation on X. And finally, you perform Buchberger reduction on the particular solution modulo the Grobner basis. This is their approach. In particular, how do they compute the particular solution? Well, they compute the particular solution by means of separator polynomials. When you have a finite set of points, P1, Pn, a separator family is a set of polynomials, and you have one polynomial for each point. And they are such that if you evaluate the polynomial at the corresponding point, you get 1, and you get 0 otherwise. In order to compute such separator polynomial, you need to keep track about the coordinate in the index of the coordinates. 2 points start to differ. So you start checking a couple of points, pi and pj, and you start from the first coordinate, then the second one, and so on. When they start differing, you have this value Cij that is important for constructing the separator polynomials, because with this Cij, you can construct a building factor for this separator polynomial. These building factors are a Lagrange-like polynomial that should be multiplied in a suitable way in order to get these separators. And the particular solution, in the end, is nothing more than a linear combination of these separators with some coefficients. The paper by Laubenbacher and Stigler also state their complexity, that is this one, and is completely correct, and it is quadratic in the number of variables and exponential in the number of points. What we want to do is improving this complexity by changing the approach. In particular, the approach that we use is the one of degroebnerization. And now I will explain a bit more what is this degroebnerization. The thing is, Grobner bases are not efficient to be computed in general. And degroebnerization says, well, let's try to limit the use of Grobner bases only to the cases in which it is really, really necessary, and try to find alternative solution every time it is possible. In particular, using tools coming from, for example, linear algebra and combinatorics. Linear algebra and combinatorics are exactly the tools that we are going to use in order to improve the approach for this program. And first of all, we introduce linear algebra. This formula by Lundqvist allows to compute the normal form of a polynomial as a sort of linear algebra step. Because if you have a finite set of points and this I of x is the ideal of points, you can compute a basis of the quotient algebra k, x1, xn modulo the ideal. And in order to have the normal form of a polynomial f, you have to perform what is done in this formula. So here you have the basis of the quotient. Here you have a basis in which a matrix in which you evaluate this basis of the quotient at the points. And here you only have the evaluation of the polynomial of which you want the normal form evaluated at the points. And then you only have, let's say, invert a matrix, transpose, and matrix multiplication. So it's a matter of linear algebra. In principle, then, in order to solve the problem, you need the particular solutions, because they are the polynomial for which you want the normal form, the set of points, and a basis of the quotient algebra. But I'm still cheating a bit because we can do better. We can do better because if you remember, in Lundqvist's formula, for computing the normal form of a polynomial f, what I need is the evaluation of this f at the points. And what I know from my problem is that f of pi, that is f1 of pi, fn of pi, is exactly pi plus 1. So I know what is fi of pj. It is given by coordinates coming from the next state. And so I already know the evaluations. I can completely avoid the computation of the particular solution and go on. I need only to compute a basis of the quotient algebra and to apply the formula by Lundqvist. So now the problem is how I compute this basis for the quotient algebra. A basis for the quotient algebra that is also quite simple to represent and quite simple actually to find is this so-called Grobner escalier. So you have a set of terms that are never leading terms, so biggest term, for any polynomial in the ideal, even a term ordering. Of course, if you have got a Grobner basis for the ideal of points, it is trivial to find out what is this Grobner escalier. But the point is, computing a Grobner basis is not an easy task. And so I don't want to compute the Grobner basis. I would be happier if I can, given the points, get a basis for the quotient algebra, perhaps this Grobner escalier, or in any case, a basis for the quotient algebra that helps me for the problem without passing through a Grobner basis. But this is possible. There are some combinatorial algorithms that take the point and go directly to the basis of the quotient algebra. There is a bijection between this set of points and the monomials that you find in the basis of the quotient algebra, so the Grobner-Escalier, and you can find this correspondence directly without passing through any polynomial. I don't have to compute any polynomial, no polynomials at all. The first algorithm doing that is an algorithm developed by Cerrienko and Moreddu, two Italian mathematicians. And this is the complexity where you have a small n representing, as usual, the variables and big N representing the points. Well, this algorithm has a good point. It is iterative on the points, but the bad point is that it's not so efficient. I mean, the complexity is not the best we can achieve. The best complexity is attained by the Lex game, this algorithm here that bases the complexity on the usual number of points and number of variables, but also by this R, that is the maximal number of points with the first coordinates in common, and then they fork. But the problem of the Lex game is that it is not iterative on the point, and this makes this algorithm to be not the most suitable one for our specific problem. In our problem, indeed, there is a lot of dynamicity, and you may have different bunch of data that come in different times. So if I don't have an iterative algorithm, well, I have my data today, I make my computation, I arrive at the end, but then if in a couple of days I have another bunch of data, I have to start from scratch, and I don't want it. So we developed an iterative Lex game whose complexity is, let's say, halfway between the two algorithms, but at least it is iterative on the points, so it is actually the most suitable for this kind of problem. What I'm going to describe now is how we compute this basis of the quotient algebra, because using this algorithm, we get the only part we still need in order to solve the problem, and then we can discuss what is the complexity of our procedure compared to that of Laubenbacher and Stigler. So, first of all, in order to develop my algorithm, I need some data structures. I need data structure in order to store the points in a suitable way to navigate it and to get data from the points. So to get information, the information I need from the points. And the same goes for the monomials. For the points, we use this structure here that actually is also present in the Lex game, that is called point tree. A point tree is a rooted tree in which you label the nodes, so the different nodes of the tree with indexes representing the points. And you label the edges of your tree with the coordinates of the points. You have one path in the tree for each point, and you know that two points share the same path from the root, so from level 0 to some level I, if they have the first coordinate, the second coordinate, the third coordinate, and so on until the ith coordinate in common. And then at level I plus 1, they fork in the tree because the coordinates are different. This kind of tree can be constructed in an iterative way on the points. So let's see an example. Here you have 4 points, and first you have only one path corresponding to 0, 0. You can see the coordinates here. Then you add P2, and you have forking level 1 because the first coordinate is already different. But when you add P3, so you get to this tree here, the forking level is 2 because the first coordinate is in common with P1, and the same goes for P4 and P2. This is the tree that you get in the end, and you see that it can be computed in an iterative way. The second data structure that we need is the barcode. That is a data structure for monomials that actually comes from my PhD thesis. And it is a diagram of this kind in which you have these horizontal rows and these small segments in each row that are called bars, which satisfy two properties. First of all, under one bar, there is only one bar. So if I have a bar here, I cannot break in the middle in some level downstairs. And also, I need that all the lines have the same length, where the unity measure for length are the top bars, because as you can see, they correspond to a single monomial. I will explain you in the next slide why. Because in the next slide, we are going to see how to associate monomials to bars. First of all, I have to remark that each level, so each row in this barcode, as a number here and corresponds to a variable. So level 1 of bars represents x1 and then x2 and then x3 with the convention that for me the minimal variable is the one with the minimal index. So x1 is a small variable, then you have x2 and so on, and xn is the biggest one. Then I take a term and I define a map pi I that cuts out the small variables. So if I apply pi I to a term, I cut out all the variables from x1 to xi minus 1. I can define it for each I from 1 to n and take a set of terms or increasingly ordered with respect to x to which I apply all my maps. In the beginning, I have a set of terms, so I don't have repetitions. And that's why I will have single bars. But when I have repetition, I only have to underline under the same bar those terms that are repeated. So I have, of course, I have repetitions because when I cut out variables, I may have the same final things. And that's why you have some bars that join more than one term. So now, finally, our algorithm, how does it work? You have a base step in which you have only one point, and the monomial that corresponds to them is 1 because the ideal corresponding to 1 point is the maximal ideal, xi minus the coordinate, and so the only monomial that is never leading term is y, this is 1. Then you have to add a new point, so you have to update the trie and take care about where is the forking level, because the level, this forking level represents also the maximal variable that will appear in the corresponding monomial. In order to know the exponent, you have to look in the trie with the rule for finding out another point that I already processed, the corresponding term, and increase by 1 the exponent. This translates in these two conditions that says, since xs is the maximal variable appearing in your monomial, you must stay in the very first bar on the left with respect to s plus 1 to n. And you have to take the s bar corresponding to your antecedent and go just to the right. The thing is there already anything on the right or not? If the answer is no, things are easy, so you don't have to do much. You have to construct a new bar in the position you want, and what you get is that your monomial is only a pure power. While if the answer is positive, you have to repeat the procedure, because you have a bar on the right, you have some points there that are associated to the monomials in that bar. And so you restrict your procedure to the new point and those corresponding to to the monomial in that bar. And you restrict also to the levels from 1 to s minus 1. And you repeat the same thing. Look for the new forking level, look for the new antecedent, look for a new bar on the right. If you arrive at a point in which there are no bars on the right, you finish. If not, you will do that when you arrive at the first variable x1, so to the minimal one. Here we have an example with the same small set of points that we had. So for 1, we have a barcode with only 1 point. Then you have P2, for which the forking level is 1. And the antecedent cannot be different from P1 because I only processed P1. So I go at level 1 here, and I should go to a bar on the right, here, just on the right, but remaining over this bar here. Well, there is nothing of this kind, so I construct it, and of course I lengthen, for practical reason, the bar of x2, and I get the monomial x corresponding to the point P2. Then I go to P3, for which the forking level is 2, and the antecedent is again P1. So I go at level 2 under P1, and I should go on the right. Well, there is nothing on the right again, so I construct a new bar here, and I get y corresponding to P3. Finally, I have to add P4, and for P4, things are more complicated, because I add P4, the forking level is 2, and the antecedent is 2. So I'm here again. I must go to the right, but I already have a monomial corresponding to P3. So I restrict my procedure to P4 and P3, getting, of course, that I have to go here because the forking level with respect to P3 is 1, and the antecedent cannot be different from P3 because there is only P3 there. It's a very small example, actually. And I try to go to the right. Here there is nothing, so I can add my new bar, and I get xy corresponding to the point before. So every time I have to repeat the procedure, what I get is something that is not a pure power. We also implemented this algorithm using C, and in particular using C some linked list of data structure that are like concatenated lists, one for the bars, one for the levels, one for the terms. And well, the curious thing is that with respect to the graphical version that I give of barcodes in a computer, you have to reverse it. So these small rectangles here represent the 4 bars that you have here, while, for example, this one is this big bar here. We made a testing activity with our iterative Lex game, so our implementation in C, with respect to the implementation that we found in Singular. In my knowledge, this is the only implementation of an algorithm of this kind, and actually the algorithm that is implemented in Singular is Chelenko-Moreau algorithm. In any case, we made this comparison of the performances, and as much as you increase the number of points, as much you get a better performances, actually. Or also, if you increase the number of coordinates. Actually, for the way we implemented the things, increasing the number of points, increasing the number of coordinates is more or less, affects the complexity more or less in the same way. Finally, complexity. As I said before, this is the complexity we started from, so the complexity from Laubenbacher and Stigler. We first observed that if you improve the way of practically doing what they want to do, we can improve the complexity, in the sense that they take all these Lagrange-like polynomials to construct a separator of polynomials, multiply them all, and then reduce. But if you decide to start with the first, make the first multiplication and reduce in this first step, and then multiply another one and reduce, you can improve the complexity going within this complexity here that is far better. For what concerns our algorithm, we get the complexity of the iterative game plus that of Lundqvist formula going into the so-called degroebnerization complexity that is actually linear in the number of variables and cubic in the number of points. So with that, I concluded the talk. Thank you very much for your attention. And well, if you have questions, I'm here. Please ask. I think we can unmute and ask.
Thank you very much indeed, Michela. Yes, there's time for a couple of questions.
Okay, if there were some questions in the chat, I couldn't see them, so let me see.
No, it's not. There's a
No?
thank you from Brandon Stigler.
Oh,
Hi,
nice to see you. Nice to meet you.
Yeah, yes, thank you. Can I ask how I think I don't understand what the role of the bars is and how you got them. I think I've seen your paper before. And I was still I didn't understand that, and I'm still struggling. So I know you only have like maybe a minute or two to respond, but could you just go back and kind of give like intuition?
Yes, and then perhaps if you need more, we may also talk by email if there is no time more. But let's see. For example, I may go to the example. If I understood the question, the idea is why I need this. Well, what is the relation between the bars and the monomials? Right?
Yes. Yeah.
Okay. Well, the thing is, these bars actually represent the exponents of the variables that you have in your set of monomials. So when I say, for example, I need to stay in this bar here, so in the bar in the very left. No, sorry, this is left. I always make confusion between left and right when I talk to a camera. Okay, if I have to stay in the first bar because I start counting from here, it means that the exponent of this variable is 0. So it means that the variable does not appear. Going to the right by 1 means increasing by 1 the exponent. And in this way, using this system of bars, the thing is you can retrieve quite in a fast way, using the exponents of the monomials that you already had. Where are the monomials that you need in that point? Because the very big problem of the algorithm by Ceria-Muredo in the very beginning was that some computations were repeated because they did not have a way to store the monomials and to retrieve where was the monomial for which point you had these monomials and what were the exponents. So the idea is probably better sketched in the example, in this thing here, that when you associate bars to monomials, you are actually cutting out small variables. So here you have the monomials as they are. Here you are cutting out the smallest variable and you are concentrating on the exponent of x2 or on bigger variables. And here you are concentrating on the exponent of the biggest variable. So I hope I answered to your question, but please, if you have some more precise problem, just tell me. More precise, let's say, question, just tell me. So the intuition is that you can navigate there to see and to reach exactly the exponents of the monomials that you really want.
Thank you so much. So the point is you're creating a Lex basis.
Yes, I'm creating a Lex basis with that. And I'm completely avoiding the problem of Lex basis to be expenses to be computed because I don't even see a polynomial. And right. I only use this trie extraction. Yeah.
And do you have any methods? This is excellent. Do you have any methods for computing other types of bases, not just Lex bases?
Well, not for now. I'm thinking about that, but at least this use of barcode is intrinsically Lex. So if we want to do that, we probably need to have to switch to some other structure or to some other idea. And also this comparison of coordinates, well, I tried it out in some experiments and so in some examples, and it doesn't go so well, for example, for graded orderings. So I think that if we want to do that, we have to change quite more or less completely the approach. Because I made some experiments with that. Okay. Is there any ordering you are particularly interested in?
Well, Lex orders are great because, you know, from like an experimental point of view, you know, an experimentalist may have a sense of which genes would be important and which genes wouldn't. So any kind of elimination ordering is useful there. Graded orders are really great if you believe that there are a lot of interactions. So the point is you want a lot of mixed terms. But those are, you know, those are pretty general. So I don't have, you know, a better answer to that.
Okay, okay. But in any case, if you are interested in discussing on that, you may also contact by email. I may. Oh, okay. I can. Do you know my email address? Probably you can find it. But oh, I have no problem in writing it in the chat. I will write it in the chat.
Yeah, yes, please do that. That's great, and I'm really glad that we've got a good interaction going here. There's time for one more very quick question.